finally, our international keynote from all the way from Geneva, Niels Linneman, who is an expert on the metaphysics of quantum gravity and Spin-2. So today he will talk to us about that topic. Yes, please take it away.
Yeah, it's preamble. Ian is a very good friend of mine.
we start now. Right? Yeah. And maybe afterwards.
Why I criticize him is because I'm interested in his work. He's careful his work. Care about his work. Otherwise, this. Let me start with three observations. A historical one. There have been incorporation attempts of gravity to particle physics from the early heydays of relativistic particle physics. Yet still, and maybe some students who can testify, it has not really come into mainstream textbooks. So there's some exceptions. Feynman lectures written down in 1995, Weinberg's famous textbook, and then also string theory book, Ortin, which all can take a particle physics approach to GR. But you probably normally learn in GR this wall, and I don't know what happened. Okay. Second related observation, a sociological historical one. This is hidden between the GR camp on the one hand and this particle physics camp on the other hand, the way how they talk and how they teach and so on and so forth. And it's also inherited when we look at quantum gravity approaches, therefore actually relevant. And then thirdly, and this is getting more to this talk because it's going to be more of a conceptual and systematic talk and less of a historical talk or sociological talk. There is an uncontroversial perturbative view of GR in the sense of regime-specific space-time thinking. And I think we can all agree on it. We some kind of perturbation of GR on flat space-time. At the same time, there seem to be all these forms of derivations of GR from particle physics, and the big question is, what is the import? What can we learn? So Ian likes to use this word Spin-2. Where does this come from? Well, the particle physics approach, of course, well, the fact that you usually do particle physics in Minkowski backgrounds, right? That's what we take to be the particle physics community in general to be doing, is then linked to a specific Bing classification. We can categorize fields based on spin S and mass M in terms of their irreducible representations of the point topic group. Okay. There's a bit of sloppy talk going on, of course, when we speak about the massless case of really mean is helicity, so projection of spin on momentum, not spin. Okay, but fair enough. Now, I think that's something we can all agree on, or we should all agree on, because I really think this is consensus in physics without much interpretational freedom, namely that GR is a massless Spin-2 theory in the sense that, first of all, as I already said, it's flat space-time expansion is massless Spin-2, so Peirce Pauli. And secondly, and maybe more interestingly, it is under certain conditions that we get a unique generalization of this massless Spin-2 theory into an interacting theory, and this is up to change of variables, GR, or at least we get the field equations up to change of variables. So what is GR? We can discuss it with us, yeah. Okay, so I'm not going to question this. This is a consensus. Hopefully, no one disagrees with this at this stage. We will just ask beyond the conceptual level, partly metaphysical, ontological level. So this is the talk for today. I will sketch what's traditionally labeled the particle physics approach to GR. Okay, this has happened already to some extent, but here's my take on this. I will demonstrate the diversity of conceptual readings at play here. And then I will try to reconstruct, in particular, assess ontological readings. So this kind of readings I take with here to be interested. I will make the distinction between epistemological readings and ontological ones. So not the threefold anymore, this is twofold. So epistemological, well, somehow interested about this reading somehow about how you can learn about GR, coming from somehow how you get to know GR, whereas this idea that no, there's something ontologically going on here that you can undergird GR, whatever GR describes stands for, with a more fundamental story, which is the Spin-2 story. Okay, and I argue against ontological readings. Okay, a bit of Plato here, since this is a philosophy talk. I guess our simple motive will be to check whether it's true what Ian says up here, that the good is the spin-2, and we are coming here out of our cave from GR, and that's basically me here also. And we will wonder whether we can actually turn this picture around or not, right? Okay. A slight remark also on representation is not ontology. So often the particle physics approach is presented in contrast to the standard geometrical story, right? So like, I don't know, walls, it's geometrical, particle physics somehow not geometrical. Apart from the fact that it's very difficult to pin down what you mean by geometry, the different senses of geometry and so on, Euclidean, Kleinian, I don't know, what have you. And there is this point simply that you should not ever mistake the map for the territory, right? What are the representational means is not equal necessarily to the representational content, right? So in that spirit, also GR has been regarded by the various people as, even though it uses geometric representational means, it does not mean that therefore somehow GR commits it to an ontological sense of geometric view. For instance, an example is LHC Einstein himself, if we can believe Linneman. So Einstein was thinking of GR as a theory of unifying. I think this was said earlier by gravity and inertia, but geometry was just a tool for doing this, for achieving this. And then we have this kind of mysterious dynamical approach, which got mentioned here also and explained to some extent. There's also it's this dynamic approach to GR, so not Kier's approach, but the original dynamic approach to GR. Brown is also a Kleinian version, like the symmetry version, so to speak, of Gomez et al. Right now. Okay, and that also just renders GR as being basically about fields like other series about fields, they interacting with other fields, and geometry is just a means of representation. Also, if you look in the gravity literature, when people actually have to kind of get away from this beautiful geometric picture of GR and quantize, and there's stressing how GR is actually very similar to other series historically to electrodynamics. Now, for instance, look at gravity to young Mills. And Rovelli, for instance, makes this case so nicely in a pedagogical book, this textbook with Vidotto, that you should really think of the G field as one field of many. And yeah, this is just a field view despite this geometric means used there. I myself will nevertheless often use the geometrical language, but then please, without any further commitment on my side. Okay, so now let's have a look at what I take the particle physics approach to be. Well, approach is ambiguous, we should go somewhere, but what does it really mean? Well, let's distinguish between the formulation, the spin-2 formulation, and the spin-2 derivation. Okay. So this is simple. We have, let's say, large inhibit action. We do a decomposition of our metric, about the background also of our fields, right? Corresponding to the solutions for the background. Yeah, we get this theory, so to speak, of something around some expansion around the background, and we can do this expansion arbitrarily well, right? So okay, you could call this the spin-2 theory if I choose now the Minkowski background. Think of this as a generalized spin-2 theory. If I don't use the Minkowski background, let's say some Ricci flat background. Yeah, okay. I can also use another background, but then I won't have a pure spin-2 theory. I should not say impure as the other spin mix into the gravitational dynamic degrees of freedoms. Okay, relative to the background. Okay, so this could be one sense how you think of as reviewed by Pedro Pitts of the spin-2 view, but okay, but this is actually just a reformulation of GI. So you're just changing the variables. You're just going from G to eta plus H, and then let's say nothing happening. But there are going to be two moves in the literature that turn this reformulation into a theory of its own. There's something about Pitts called, I call this minimal SRGR. Okay, you specifically focus on this Minkowski background. You don't even take this Minkowski background to be a metric. You think of it as some reference structure. And then you think, oh yeah, this is now a different theory because it has this terribly different interpretation of GR, at least by GRs. Okay, maybe more interesting is this causal, what I call causal special relativity GR. Again, Minkowski background, we really as a metric first of all, and now impose that this effective G field, so G is supposed to be eta plus H, right? There's this G field now really lives on this Minkowski background eta, which however means that this G field has to respect the causality conditions, that's the causal structure of your eta field. So when in a picture, you want to have some idea that of the following realized that when you say fundamentally there's this Minkowski background, there's some H field on this, if you get an effective metric from this, so G equals eta plus H, this G somehow still respects this background metric. And so yeah, you don't want to this G, so to speak, with its cone to get out of the cones of the eta background. Okay, this I think is physically more substantial, less just plain words, and let's call this causal SRGR. Unlike minimal SRGR, this causal SRGR captures really a common understanding of GR and SR, which is testified by criticisms by Penrose, effectively directed against such a view called, I think, Lorentz covariant GR at that time. And this is in some volume back in the 80s. Okay, so that could be what you mean by the particle physics approach, but actually what people mean often are these derivations somehow. Okay, so we've already heard very nicely about the self-interaction approach. Yeah, so you start with free mass to spin-2. What happens if this was sourced by matter? You take the spin-2 series somehow to be a zero gravity. Somehow it's supposed to couple to matter in the reverse way. If you go to the quantum, actually derive this even, so argue for this better. But anyway, that's the idea. So you put something on the right hand side of this Fierce Pauli equation. So I will not repeat this because we already had this earlier, unless there's an urgent question about this. Okay, so what's important here, the energy momentum tensor should be that of special relativity because we're starting with that background, it seems. But this is highly ambiguous. It's highly ambiguous which energy momentum tensor to take because you can always change this with superpotentials. However, for this coupling to an energy momentum tensor where you can change it by some current, you can change the current by some potential. This has real effects on what theory you actually end up with. I will explain this a bit more. And there's this very eclectic version of this bootstrap, which just runs in effectively one step by laser, which people really like. What's important to point out here, it hasn't been mentioned, you can also do this for other spin series, so spin n. So not just for spin-2. Okay, what's maybe interesting to mention here is also that, so to speak, tool, maybe not that formally speaking, but somehow so to speak, as a counterpart to this self-interaction picture, I can also have a gauge deformation picture. So I can start with my spin-2 free mass and spin-2 theory. It has a kind of gauge group. I can wonder about its deformation, especially what its deformation look like if it became interacting theory, no matter what the interacting theory is supposed to be. And it turns out that this will be highly constrained just on how this gauge deformation works of this initial gauge group. And I can thereby, with a few conditions, get from free mass with spin-2 to GR. That's what's the state of the art result here. An assumption of locality, point covariance. Let me drop some things. What I mean, the implication I get Fierce Pauli on the limit. I only work with up to second derivative. I can only have basically collection of spin-2 fields or and or a sum of independent Einstein-Hilbert actions starting from collection of free mass spin-2. Okay. I could illustrate this a bit more, but I'm not sure. I think, let's say, the toy model of spin-1. Maxwell equations, you have gauge symmetry, system divergence, right? And if you now look for the interacting theory, take this that if you span this in its lowest order, it's supposed to be lowest non-material order, it's supposed to be Maxwell. Then what you find is that you get constrained from different orders in an expansion of the A field. And so basically there are many questions which determine, thereby over-determine different how you say, expansions of the A field, and so you get strong constraints towards something, and you can exploit this with some conditions to actually derive the generalized gauge group, and from that, such theory we end up with. So that's basically the route from Maxwell to young Mills, and you have an analogous route from Spin-2 to GR. Sorry, this is very quick, but I want to talk about the philosophy, so we can talk about this in the Q&A. What's interesting, even here, there's a bit of a uniqueness question of, well, for higher derivatives, once we don't just work with second order derivatives anymore, but higher, we can definitely show that will not be unique anymore. Otherwise, it seems to be relatively unique, but maybe this approach was more constrained from the get-go than this self-selection approach. Okay. Okay, maybe it was also important to mention, I will not go into much detail here either, is that you have this quantum variance of this. So, especially in the S-matrix formalism, it has been shown that you can, first of all, derive the universal coupling property of interacting Spin-2, that you can derive that you should couple to actually what's energy momentum in the classical theory. Yeah, but what remains also there is this ambiguity in energy momentum. I just want to stress a point here, which I think Kian does not stress enough, that this also works in the non-flat backbone case. So it has nothing to do with Minkowski or this going to S matrix, that you can actually get, for instance, this idea that the interacting Spin-2 has to couple to the energy momentum tensor. It has been shown by Davies and Farkowski that in action formalism, that also for other backgrounds, out of consistency, you need to have coupling to energy momentum tensor. Yeah. So kind of this idea that it's low its invariance, which together with consistency enforces, so specifically low its invariance, which enforces together due to consistency universal coupling for the interacting Spin-2 theory. I think this is a wrong way of putting it. It's just whenever you want to have an interacting theory starting from Spin-2 about whatever kind of background, then in order for this to be consistent, it has to couple to energy momentum tensor, or has to couple universally. So it's not about the Lorentz invariance specifically. And then there are also variants, for instance, of this gauge duration I pointed at for the quantum context. And I think effectively work very much the same like in the classical context. Okay, what we keep in mind is there are two major ways of getting generalized regularity to GR. Self-interaction versus gauge approach, not so much a question of classical versus quantum. Both work for other backgrounds and for other spin theories. Now we do a bit of history. So pseudo history, we follow the right timeline, but we won't really dig up in the details of where this gauge now came from and so on. So everything has to be taken with a grain of salt, but it gives you an impression what you see when you read the literature. We start with the early days of 1955, where Quaechnan and also Gupta more at the same time would put up the first derivations, GR and Spin-2. What he says here, the principle of equivalence, the associated geometric postulates of generativity are abundant as a foundation, and instead a starting point is taken which employs concepts closer in some respects to those which have been found pertinent to microscopic physics. So there's a bit of a flavor of unification here, but put it into a similar framework. Gupta, Einstein himself, and others have tried to construct a unified theory of gravitation and the electromagnetic field. We also see that the main difference between the two theories can be attributed to the fact that while the Maxwell field corresponds to particles of spin 1, the Einstein field corresponds to particles of spin 2. Okay, sorry. Feynman stresses how people try to geometrize electrodynamics, but now it seems to be the other way around. People like I mean, now it's a days to take a different approach, more suited to meson theories. We have gotten used to the idea of fields, so it's not a problem to actually think of all this collection of fields. So this original idea of the Lutzer Klein, while geometrizing, is now thrown out. Let's rather try to make everything into fields, into the particle physics suit, if you want. Okay, it's also Feynman. So these three things were about the theme of unification, you could say, who then brings up this idea of that this Spin-2 approach is a like alternative history of how you could have arrived at the Einstein field equations. Alternative history, if you want, or rational reconstruction of fictional case. So imagine people on Venus who are good at QFT, haven't found GI yet. Wouldn't they go through this zoo of 0, 1/2, 1, 1.5, 2 spin particles, spin, and so on, and then they just construct from that GI in some way, because they need to find also something consistent. So once they are asked what is the interacting theory, don't they also write there? Okay, that's another theme, so to speak, theme of rational reconstruction / alternative history. Weinberg brings in the word of logic here. So for the logical structure of physics is often anti-parallel to its historical development. We should revisit this kind of allegedly geometric presentation of Einstein and so on, because we already see that from the input, and maybe like this, strictly speaking. And we should wonder, is there a different way to construct the edificio of physics, and maybe not why not via this particle physics approach? So Weinberg makes the case, right? These are another important figure here. It raises the question of whether this a priori aspect of initial geometry, I mean, in this case, flat one, can be removed and replaced by an arbitrary spacetime, but still keeping the non-geometric disputable derivation. This just to show that people are really contemplating also other backgrounds. This is, and they're actually successfully contemplating these. And here I think it's a very interesting one, which carries us towards Kian, towards the ontological, because it is said that from this point of view, this particle physics approach, Einstein's theory is an essentially phenomenological, albeit unique, theory for describing interaction at macroscopic distances and time. So this suggests we a picture somewhat GR-ish, and then undergirded by somehow Spin-2-ish waves of modeling / thinking / representing. Yeah. Okay, and here we come to philosophers, and the bread and butter of philosophers is, of course, conceptual clarification. So some of these statements maybe we can read in passing and wonder whether people really believe it, but the philosophers, they really commit to that. That's the only thing they do, that they clarify these positions, and therefore I think we can take it much more straightforwardly. So Lemko has also this offers this idea that there can be this Spin-2 approach, which we read as providing for an effective reading of the metric field, right? It can then be argued that the full metric G is only an effective notion, and that remains fundamentally spaced on geometric eta and the gravitational field H separately. The gravitational field would be what makes effective metrical space G derived from its actual metric eta. Notably, it was also careful to point out that there could be a heuristic reading of this, so just to be fair to the next step. And now we come to Kian. So Kian presented times Spin-2 bootstrap explicitly as a form of theoretical and also ontological reduction. So if you say a theoretical relation, it's theoretical reduction. This is how one theory relates to another, and one subsumes, if you want, the other. And if you say this to be ontological reduction, then somehow it takes to be there a corresponding relation between what one theory represents and what the other theory represents, right? So like a table gets, let's say, ontologically reduced to, I don't know, its atoms or so. This gets theoretically described as a corresponding physical series. What have you? Okay. So Kian would say that all of this allows for complete ontologic reduction of relativities, metrical structure to matter field structure. So yeah, I think we've heard this enough. There's Pitts issues caution, but I think we have had enough of these voices. Let's continue. So, okay, again, this is not to suggest that the physicists necessarily all think like this. I think the philosophers can think more about that. I mean, for Weinberg, it's also known that at some point we tracked it as strong geometrical commitments, anti-geometrical commitments, sorry. As I've learned from some exchange between Pitts and Weinberg, but sorry, that's an example. Okay, so we've had as the Swedish would probably say, a smorgasbord of, it's also misspelled here, of readings. Well, we have on the one hand this epistemological track, so Spin-2 approaches a guide motivations towards the field equation, so rational reconstruction, alternative history, some structural insight about the inevitability, maybe robustness of the field equations. So maybe in the spirit of the Lovelock theorem, which some of you probably know. Okay. And then on the other hand, we have this idea, oh, maybe there's a new perspective given to us with the Spin-2 approach on what is fundamental, what are the dependency relations and so on. This is here, for instance. So, okay, so then the question is, do we have this plain vanilla logical reduction of GR to spin 2? Do we have something fancier, maybe some dynamic reduction? Do we have something which I call design reduction? We will explore this. Okay. So I already distinguished between topological reduction and theoretic reduction. They're first of all dependent. But of course, a lot of the discussion in philosophy of physics happened in a realist corner. We're all kind of thinking that it's at least in some way physical theory represents something in the world, right? So yeah, so not anti-realist, but yeah. And Kian is definitely a realist, right? I think that's fair to say. And so take on Kian, we can also take on take up a realist language. Now, you can explicate scientific reduction, also then corresponding to logic reduction in various ways. Classic is Nagelian reduction, and this known as Schaper reduction, and the functional reductions, and also all kind of things, the level of the theory, the level of the model of the succession, the physics historical level of the solution of the theory, doesn't really matter. That's it's all that. Now in physics, what we do normally, we just take a limit, we say, oh, this one reduces to the other somehow, right? Okay. Now, this can, of course, be brought into contact with these philosophers' notion of science notion of reduction. But first of all, what we see, if someone claims theoretic reduction, logic reduction, there is no clear, straightforward sense of limit here in this reduction of GR from spin 2. If you go from GR to spin 2, there's a clear sense of limit, and this was Manus pointing out, it's a nice expansion, but in this theoretical / logic reduction of GR by spin 2, so that does not involve limit. So, but we might say, oh, maybe there's still a way to think of this theoretical reduction of the spin 2 case as some form of reduction in the philosophical sense. Maybe it's not the limit sense of physicists, but maybe still Hegelian, Schaffnerian functional reductions apply. Yeah. Okay, so as an example, take Hegelian reduction. That's basically this idea that the laws of one regime are derived from the laws of the other regimes together with some bridge laws, right? So I have kinetic gas theory, it's underlying theory. I define temperature as equals to average velocity somehow correctly squared, right? This is my bridge law. In arguing this is analytic, this is experiment, this is empirical. I can argue about its nature, doesn't matter. And then I derive now from this original theory plus this bridge law, I try to derive thermodynamic state of that section. Okay. Now the thing is, neither the bootstrap nor the gauge argument work as a logical argument and things like that. Again, contra what you have with the GR case. So why is it? So what you need is kind of a schema of mass plus Pierce-Pauli plus bridge laws that entails somehow GR, derivation, deduction. But what you have is Pierce-Pauli plus constraints that generalize uniquely to SRGR. So the formulation of GR around the background. And then with this idea of setting G is equal eta plus H, set called by Kian bridge law, you obtain GR. Okay, and basically this problem of not being able to reproduce this, not being able to be of this form, no notion of philosophical reduction applies this. So okay. So maybe what's meant by here, or what could be meant here rather in general, is that you want to think of the reduction at the level of SRGR versus GR. So you want to say somehow SRGR subsumes GR. Maybe if this doesn't straightforwardly work, so it's not true. The sectors of GR cannot be subsumed like this, but it subsumes SRGR, maybe subsumes GR in its relevant parts, in this kind of empirically relevant part. I mean, here I was pointing out correctly that the globally cosmologic part of GR can be most likely be reproduced by SRGR, and that's where you could say SRGR reduces the decisive sector of GR. Okay, maybe it doesn't. Okay. Now the question is, first of all, from the GR point of view, why prefer, of course, a specific sector, which is which SRGR can successfully reproduce GR? Okay, empirically maybe, but it's really not clear about this. And also, what if you do it like this, if you think of SRGI somewhat more fundamental, because that's what it actually means to say you reduce within the other theory, you kind of become very revisionist of much practice happening in physics after the 70s, you could say. Look gravity, for instance, right? It doesn't work with the flat spacetime record at all, right? Okay. So is there some argument for preferred flat background nevertheless you can make if you want to use SRGR to subsume GR, if you really want to make a case that SRGR is somehow more fundamental? So is there some argument for why you should really believe that this flat background is fundamental? I mean, independent of how you really think of this flat background, whether you think of it as codification of symmetries or so on. So first of all, it's true that only for flat backgrounds, a bit more general for Ritchie flat backgrounds, you can have pure spin-2. So if you're kind of a purist about spins, particles, so to speak, then you could say, yeah, that's the reason for me. And you might have dynamic approach tendencies to think of Minkowski somehow being better admissible to the dynamic approach. You might like the idea of unification. The particle, some model is so far formulated in a flat spacetime background. So let's do this also for gravity. You might like the fact energy momentum tensor is probably conserved only in flat spacetime. You might have some extra claims from quantum theory to offer. Quantum field theory, of course, also normally defined only relative to. I mean, not true, but we often think it's just defined relative to flat spacetime. Of course, there's QT, curved spacetime, and so on. Okay, I would open test all of this. That's somehow not helpful. Because I would think spin's just a classification. It's useful in regimes where it applies, otherwise it shouldn't be. But yeah, so concerned about this dynamic approach I want to highlight works for GR also in some way. I mean, in two ways actually. In the Brownian way, and you might not like it, that's true. And maybe you think of Ian's symmetry approach is more elegant, but there's also a local version of this one. I like almost it. Yeah, and the unification, I think you had a term, right? We call this not intermediate unification, but
restricted.
Yeah, exactly. So we have some kind of restricted unification here. That's okay, but that's true because we haven't been doing some modeling in curved spacetime yet, right? We build our accelerators. I mean, this is for regimes where we don't have influence of gravity. Yeah. Okay, and so on and so forth. Okay, but now I want to be more charitable. Right? I want to see maybe there is, after all, something I'm missing by telling the story like this. So just recall, we have this list. The derivation is being good way for doing a theoretical reduction, ontological reduction. We have had our doubts that we need to reduce GR from, or should reduce GR from SRGR. Now there's maybe something we're missing, and one option is we are missing maybe something in this dynamic picture of having spin-2s interacting with each other. And the other idea is maybe we should really think of how Ian provides us with these derivations differently. Okay, let me expand. Okay, so maybe the idea should be think of GR as fundamentally describing this coupling of these spin-2 particles. A process which then gets mathematically represented through metric description. So it's you can come with all kind of formula and relations and so on, but the important thing to grasp is really there are these messenger particles and they're interacting, and that gives rise to something I can effectively describe by GR. It doesn't matter what you just showed me earlier about this Magdalian and Chapmarian schemes of reduction. Okay. Now, first of all, if we take such a picture, then this also applies for Young-Mills. And we should also think of Young-Mills as somehow being the corresponding bosons interacting. And Young-Mills is just an effective description of somehow self-interacting bosons. Yeah. Okay. But this is maybe not a problem. But it's just we have to kind of change a bit how we think about the world, I guess. Maybe some people are always thinking like this. Okay. Now we come to this dilemma again, which Ian put up. So I would think it's either unclear to which of the many possible energy tensors the field is supposed to couple in such a dynamic picture, or if we don't think of the coupling in terms of energy momentum, but just somehow brutally of the field to itself, yeah, it's unclear why we should do this in the flat spacetime. And let me let me expand. So on the socks in the second horn, if we don't allow ourselves to energy momentum tensor notion for saying we're coupling to when saying how the feed gets coupled to something, but just feed couples to itself somehow. The question is really why isn't it true for all other backgrounds? I mean, then also you can think of the field coupling to itself and so on. And we're in a worse situation in the static, non-dynamical situation, because now can it really be that we can just use non-empirical readshoes to decide between whether this mechanism or that mechanism is true? Isn't it that somehow on this picture, somehow the world is fragmented, and it's both true that somehow the metric field is actually the result of these kind of particles interacting or relative to that background, and these kind of particles interacting, I mean, still between two particles, but relative to different backgrounds, interacting with each other. Yeah, so this I think strikes me very attractive. And on the first one, so if we think we should have a coupling to energy momentum tensor, then arguably somehow place based on is preferred because we have a good notion of conservation. We don't have any other background. Okay, fair enough. But then again, you have this problem of ambiguity, and I won't annoy you with this for too long. It just turns out if you have different choice of energy momentum tensor, you get different predictions, for instance, for the perihelion of Mercury. And interestingly, you don't use, and this might be a bit suggestive, and maybe not a bulletproof argument of myself, but it's really, it's not the canonical, not the Bill-Fante, not the Rosenfeld energy momentum tensor you use, but it's exactly one you get from linearizing the prescription from GR, which turns out to be the right energy momentum tensor you use, or you have to use. And that seems, yeah, somewhat unattractive, I would say. I can spell it out a bit more because, first of all, this energy tensor will be non-standard. It's not what we usually do in other field series to get energy tensor. So it's not even you're not even based on just the Noether method anymore. If I remember correctly, I think that's true. Yeah, and there's also this issue that somehow the field needs to know to which energy tensor it really has to couple, right? It's a teleological element to it if you talk in the logical terms. Okay, so I mean, this might be a bit strange, but the nutshell is simply here. The dynamic picture gets into this dilemma, and yeah, both forms don't strike me as attractive. We can discuss this more here. Okay, and then here is a radically different one. So maybe what I forgot or what I overlooked is how much attention Kian, not Kian here, but Kian wrote his book, paid attention to the derivations, the nature of the derivations. So in his book, I would argue the derivation played a big role, and maybe we didn't exactly enough appreciate it yet. So maybe there is this idea if you have this kind of spin-2, master spin-2 objects, which get represented by spin-2, and now you're wondering what happens if they put together with matter into one box. What kind of worlds do I get out of this? I mean, it's a bit like when you're baking something. If you put some ingredients together, what kind of bread, what kind of cake do I get out of this? It's different from wondering about, oh, give me this bread and this fly, what kind of raisins are in there and how it's layered and so on. No, it's about maybe a design. It's maybe about a construction, what Ian is trying to tell us. So the idea, quite radical, arguably, think of fundamental ontology, an analogy to a design model for target X, construction model if you want. It tells us how one can build this X, as opposed to a structural model that tells us how X is actually built up. Okay, so again, the baking a pie, it's not from me, it's from Kian. I will quote him in a moment. And yeah, then maybe really think of, as I was saying, the H and body, as Manuel asked the question earlier, what was this H and G equals eta plus H? We start with the H from Pierce-Pauli, really from Pierce-Pauli, and we put some other matter from place together, and we're wondering if we, so to speak, bake it, what kind of CO do we get out of this? And then we get a different H as a result. We get the H, which is this H, V, and G eta plus H. So we really get this H, if you want, which you get by just subtracting the Minkowski metric from G, right? We get a different H, and that's how we should think about ontology. So So this is from the literature of relative science, where these design models have become fancy. So design models are not evaluated in terms of how well they represent the phenomena. Instead, these design models are evaluated based on how well they specify how some states of affairs should be. An acceptable design model indicates how to best make something. Okay, so I think here can be construed at times, at least, as providing this design ontology of GR. Otherwise, he champions the reduction to SRGR, I would say, something with a dynamic ontology flavor. And why do I believe this? Well, because this argument from Brent that you should care about what is fundamental, not what exists, and well, what is fundamental, what is derivative. Well, that's decided by the particle physics derivations, which show that H is more fundamental than G. So, okay, it's not happy. So we have this infamous God metaphor, of course, of metaphysicians here, but it gets completely new reading in this context. Because let's look again at the baking metaphor. If I mix flour, butter, and sugar and bake it, I obtain traditional British pound cake. If it starts with the same ingredients plus lemon juice, I obtain something else, maybe a lemon cake. I do not end up with both cake but one, and only the lemon cake is real. Okay, that's okay. So in contrast, we can read this as a design reading. H is determined by Fitzpauli. It's the H together with some assumptions, which allows for determining building our GR. I mean, when I say H and this builds GR, I mean H of course stands for something, represents something, and this builds up something which then is represented by this H in G equals beta plus H. Okay? And we have the structure reading. H is determined simply as an SRGR. We discussed this already. Let's just explore this here. Only on the first option, I would say, both the God and the pi metaphor together are adequate. Only on the first option does it make sense to talk about still something to be forced like here. As the essence of our backbone. Okay, but are we satisfied with such a design ontology? Is this what we would like to hear about as naturalized metaphysicians? So metaphysicians who kind of think about ontology, what is there in the world, based on our best physical theories. Well, you could say it might already be quite naive what we do in such a field of philosophy, that we try to look for the right, so to speak, absolute non-contextual, interest-independent structural ontology of the world. But why now expect it to be one unique design ontology? That seems maybe even weirder, I would think. And it's not just I say it's weird, but I think it can back it up. I mean, just in the Spin-2 context, you could, for instance, also wonder, couldn't I bake my Spin-2 theory differently, like via causality conditions? See Herzberg and Sandora. Couldn't I bake GR in general differently by starting with some empirical observations and wondering, with consistency, what does this give rise to? Okay. And ultimately, the question is really, what is the difference of telling these different stories of making GR from a rational reconstruction, right? Or for some kind of alternative history, how is it different from an alternative history of building up GR? Okay. Okay. Sorry, I hope this was not too quick or too third. I intended the demystification of the Spin-2 approach that goes beyond technical critique, so famously Panaman, for instance, or point conceptual criticism in our very limited, short 5,000 word criticism. In particular, I wanted to put its ontological readings under scrutiny by giving them as a fighting chance. That's why I came up with maybe slightly unorthodox forms of true ontology, including this design ontology. Okay, and then at the end, I would like to conclude with that it's not all bad. The particle physics story remains beautiful, but so qua an epistemic ascent, right? And so we end up with this picture now here, I would suggest. So yeah, thank you for your attention.